input, we cannot just connect the output back to the input, because it's going to create a noise instead. If you connect the NOT gate like that back to the output of a NOT gate, just back to its input, you're going to come out, it would come out not zeros and one, it would just come out random noise in something in between. So it's not a binary anymore. So what we do is that we're gonna have something more complicated than just connected that back like that. We're gonna have something like flip-flop instead. But so to know how the flip-flop works, you have seen this before in the previous class, is that you need clocks, right? So what the clock is, a clock is just a signal that is a square of waves, right? That it generates the equals, zeros, and ones, and it has cycle. One cycle is that it has half zeros, half one, and it has rising age. Rising age is when the clock changed from 0 to 1. So it's very precise. It's at this moment only, 0 to 1. So, and then it has a falling age. So it depends on the circuit. It can be worked by the rising age or falling age. So it's at this precise moment only, right? It's at the age of the clock. So the clock signal is something that is periodic. It gives us the synchronization of the whole circuit. We know how big the clock size is by saying what is the frequency in hertz, right? So hertz is the number of clock cycles per second. So, and then we can find the size of the period of the clock. Is that how big is one cycle, right? The clock is 1 hertz. It means it has 1 cycle per second. Means that in 1 second you have 1 square wave only. So it's half of the time is 1, and then half of the time is 0. Okay, so of course that is too slow. So what we use right now, our laptop is 1.5 gigahertz. So it has like billions of cycles per second. Like 10 hertz has 10 cycles per second. So 1 period is 1 divided by the frequency. So the period is equals to 0.1, right? So this is the size. It's 1 cycle has the size of 0.1 second. So the clock and the reset is a special input. Okay? We use that to control the flip-flops and all the circuits that we use, right? It's synchronous, means it has the clock signal. So the D flip-flop has only one function: store the data whenever the clock is rising or falling. So at one specific point is that either the rising, so let's just say we all use the rising age now. So at this point, this D flip-flop can store the data. So it's gonna read this D in and save it, okay? So whatever change between this clock, doesn't matter if the D is 0 or 1 between this period, it doesn't save, right? So it only saves the D in when it's the rising age only. Say if D is equal to 0 here, it reads the D in the change here, it doesn't matter. So output Q, let's say have D like here. The output Q is going to change only when there's a rising age. Okay? So rising age here, you see D is 0, so Q is 0 here. Okay. And then even though the D changed between the clock, it doesn't matter, it doesn't store. It's just read the numbers whenever the clock is rising. So right here, so D is 1 here. So Q changed to 1 here. And then at this age, D is 1 still. So Q remains 1 until the next clock, then it reads in. So Q only changed when the clock has changed from 0 to 1. So at the rising age only. So this is all the D flip-flop does. It stores the number only when the clock is rising, it's changing, okay? And then we can write down the truth table of the D flip-flop like this. So input D, right, changes. And then Q is what's stored in the flip-flop before, right? Q is the current data. Let's say it's like this. Q is the current data in the flip-flop, and D is the input, right? So the next Q is going to change whenever the next clock transition. So this truth table only happens when there's a clock transition, okay? So Q bar, Q prime. So Q is going to change when there's a clock transition. So let's see, Q is 0, input is 0, so no change, right? So here, input is the same as what already stored, so Q doesn't change. So 0, 0, 0, right? So it's 1, 1 is 1, okay? It remains 1. But if Q is 1 and then the input changed to 0, then it will change to 0 only at the clock rising age only. Okay. If Q is storing 0, the data came in as 1. At the rising age, it will change to 1. So the D flip-flop only store the data at the certain points in time, is that at the rising age of the clock cycle. So Q can feed the output of the flip-flop back into the input function. We can do a lot of things with it, okay? So it gives us the state. So it has clock and then it has time. So it means that at certain point in time, there's a state of like all the values, right? So you have states. See, with one flip-flop, you have 2 states. So you have state 0 with state 1. If you have 2 flip-flops, then you get 2 bits, right? You have 4 states. So it can have 0, 0, 0, 1, 1, 0, and 1, 1. So we have 4 states now. Accordingly, so if you have n flip-flops, then you can do 2 to the n states. So let's do the digital input, that if you have 4 bits inputs, you need state machine. But this is the example of just 4 states, okay? 4 states, it means that you have state 1, 2, 3, 4, and then when you have input coming in, it changes the state accordingly. So this is just the example of the arrow, is just that if the input comes in, the state change, right? So it can be like if you start at state 1, you have some input coming in and then it changed to state 2, or some input makes it, you go to state 4, right? So you use the state machine as to describe how your function works, how your circuit works, how they change the states. So it has a set of states that a circle is 1 state, okay? And then it has the rule of transitions, is the arrows. So this will say as a circle, as this 1 state, and the arrow saying that when whatever there's something happen that caused the transition, it will change the state, okay? And then you have the output that depends on the state. it doesn't have to be the same number as the state number. You can say that state 1, the output is 3. The state to the output is, there's no 3, so it's 0, it's 1, 1, right? So at the state 2, the output can be like 1, 0. It doesn't have to be the same. It's a function of the state number. So it can be, so you can have a solution, you can write the solution to any sequential problem. Like the previous thing is that if you have events coming in, you can write down everything that could happen. A system that you have input A, and then A change synchronously, and then whenever A is 1, 3 cycles in a row, then output will be 1. Okay, let's say if A is 3 cycles, it's 1 for 3 cycles in a row, then the output will be 1. And then when the output is 1, it stays 1 as long as A is 1. If A changed to back to 0, then the output will change to 0. We start by drawing like the first states, right? So there's nothing happened yet. So we start at 0. Okay. And we see we want the output to be 1 if A is 1 for 3 cycles. So it has to have more than 3 states, right? It has to count when if A is 1 yet. So if A is 1 for 2 cycles, if A is 1 for 3 cycles, so A is 1 for 0 cycles. This is 1 state, right? It has to be A is 1 for 1 cycle. A is 1 for 2 cycles. And then A is 1 for 3 cycles. So this is what we have to save. We have to memorize, right? This is the history that we want to draw as a state machine. The output is going to be 1 only when A is 1 for 3 cycles. So output is going to be 1 here only, and the rest will be 0. So this is what we're trying to design. Okay. So from the start, we have start always, and then we have state 0 where nothing happened yet. And then if something happens, so here we have only 1 input, so we have A, right? So A, if A is coming in as 0, you do nothing, right? Nothing happened, you stay the same. So we have the arrow saying that the input A is 0, and we don't go anywhere, we just stay here. And then if A is coming in as 1, we want to say that, okay, the A has come in 1 for 1 cycle already. So this is the state 1, say that, okay, A has coming in as 1, so we store that this is A 1 cycle already. And from that state, if A turns 0, if the input A is 0, right, we go back to the beginning. We go back to state, oh, there's no A yet. It's the same as the previous state that A is 0. Okay, so no A yet. Okay. So we put the arrow here saying that if A is 0, then we should come back here. Because we don't care about it, we just want to keep track of A as 1 for 3 cycles. Okay. But if A coming in as 1 again, so it means, okay, here you have A is equals to 1 for 2 cycles. So you have a different state. State 2 is that where A is 1 for 2 cycles. But of course, at this point, you have A can have A equals to 0, right? So you have to write down whatever can happen. What are all the possible inputs or transition that it has? So at this point, if A is 0, we should go back to the beginning. So saying here, if you have A is 0, you go back to the beginning. And if there's another A coming in, there's another 1A. Then you go back to the state 3. It means that you have A as 1 for 3 cycles already. And here, the output should change. So output here should be 1 here. So you have to fill in the rest. Is that what happened if A is 0? Okay, from here, if A is 0, you go back to the beginning. And if A is 1, it says you just stay here, right? So if A equals to 1, it should stay here. So every cycle you check the value of A and then you transition the state accordingly. So output is 1 only in state 3 only. And if it's ever 0, we go back to the beginning and then of course the output is 0. So the state machine is very important so that we can design the circuits. From the state machines that we have, then we can write the truth table out of it. So we have 4 states, okay? So we have 4 states, so we need 2 flip-flops to store the states, right? So the state has to be 0, 0, 0, 1, 1, 0, and 1, 1. To write the truth table out of it, so you just describe all the possibilities. So if the state is 0 and then input, the A change, right? And then you write the outputs, okay? So here, if the state is 0 and then the input A and 1, so we go back to our state machine. Okay, if the state is 0 and then the input A is 1, the next state is going to be 0, right? So you fill into the truth table saying the same thing. So if 0, input is A, and then it stay at this same state, which is 0, 0. Okay, and output is only 1 at state 3, so we forget about it now. Now it's always 0. If A is 1, then we change the state from 0 to 1, right? So we fill in the truth table accordingly. So just look at the state machine and then fill in the truth table, saying if it's 0 and then the A coming in is 1, then you have to transition from state 0 to 0, 1 here. And then the output is 0. Same. The next one is that when you are in state 1, and then the input A is 0. So this is easy state machine because whenever you have 0, go back to state 0, right? So you can just fill in. If whenever A is 0, you just go to state 0. So here, from 0, if your input A is 0, you go to 0, and then the output is 0. Same for the rest. The next one is going to go to state 2, right? So you feel that this state 2 is 1, 0. And then the next one is 0. So of course it goes back to the state 0. In state 2, you have another 1, you go to state 3. And then the last state, you just look at the state 3. And then if 0, you go to 0. If it's 1, you stay there, right? So you stay there. The last one is that if it's 1, you stay here. And then the output is 1 here. So outputs only change according to the state you're in. Because it change only the next state. Like the output is according to the current one right now. Like this output is gonna change when the current state is changed. So this is not changed immediately. This is like it changed the next one. Like it's actually the function of inputs here. So output is equals to the output is the function of the inputs, right? So it doesn't matter here yet. This is only one when Q1, when the state is 3. It's the Chulalongkorn machine, so the output is going to change in the next clock cycle. But now it's just the function of the input. So it depends on the input here. The current state is state 3, 1, 1. So you can, so it's still 1 by now. Like if you write the equation, the output is gonna be equals to the state 3 only, right? So it's gonna depends on the state 3 only. So state 3 is Q1 and Q0, 1, 1, and Q0. So it's only 1, 1 when the state is 3. And then the output is going to be the function of the current one. So it's gonna be function of what's already inside, which is here on the side. I know the D and Q were confusing. Let's just say that this is a current state and this is next state. So this D here, you're gonna have D flip-flop here, right? And it's gonna be D1 and D0, right? And then you have D1 equals to input A and with Q1 or Q0, right? So you have A here. A, you have to end with the Q1 or Q0. So you have here Q1 or Q0. So when you draw it, you're gonna have Q1 or Q0 here. And then you have this, let's say X here, X, right? And then you put A and with the X there, let's say it's connecting, okay? And then you're gonna have to put it back here to D1, okay? So remember that D flip-flop only change the value when the clock rise, right? So this is something that happened between the clock. It's gonna go through the gates between the clock and come in. And then it reads again next time in the next stage, okay? And then the output is from the Q1 and Q0. So the output is changing right now. I mean, the output is this one, Q1 and Q0, right? So right now, it's going to be the value of the current thing in here, right? So it's the current value that's stored in this 2 flip-flop. So whatever comes next, it hasn't come yet. It's still here. It hasn't read into the clock yet. It has to wait till the next clock cycle. Confusing. So it has to have like a timeline of like a long clock cycle. And then like this thing is according to the clock right now. It's changing at the same time. So it hasn't come in yet because it's still in this period. You have to see it in action, I guess. Right now, it's between the clock. So the value here, when it's transition between state 2 to 3, right? So from state 2 to 3, it has a function, right? From state 2 to 3, it only changes when from 2 and then input A is 1. So between that, what's stored here is 0 and 1, 0, state 1, 0, right? State 2 is 1, 0. So output is a function of Q 1 and 0 and together. So it is equal to be, it's going to be 0. Only until when it changed to the state here to state 3, when it's state 1, 1, then it and out. So output is according to these two flip-flop and together. Like the states here. Yes. So this is 0, 0, right? It's the two, the D flip-flop stores the state, yes. So output is a function of the state. It's the next state is going to be. So we have the current state, like right here, the current state is 0, right? And we say like, where are we going next? We call it Q. So from 0, 0 to 0, 1, we say like, the current state is 0, then the Q that is going to feed back in, it's going to change to 0, 1, from here to here. So I think the Q and the DF is confusing, right? Just look at it as current and the next. So it's a current state, like 0, 0, where it goes next. Depends on the input A. If the current state is 0, input A is 0, then it goes to 0, 0. Okay. If the current state is 0, 0, and then A come in as 1, then we transition to 0, 1. Yes. If the current state is 0, 1, and then input A is 0, so whenever the input is 0, it goes back to the state 0. And if A is 1, we advance to the next step, right? From 0, 1 to 1, 0. So from state 1 to state 2. If we are at state 2, which is 1, 0, and then A coming in as 0, then the next one is going to be 0, 0. So we use the flip-flop to store the states, yes, and then we change only when the clock rises. The last state is 1, 1. So the next state is from 1, 1. It depends. So we say that from 1, 1, if it comes in 0, it's just go back to 1 to the state 0 again. So it goes back to 0, 0. But then if it's still 1, A is 1, so we stay here. Just stay at the state 3. So the output depends on what's in the flip-flop. So if the D has 1, 1, then if it's in the state 3, so this is just one circuit that we say that the output will be 1 if we have A for as 1 for 3 cycles, right? So it means that if it's 3 cycles, then then the output is 1 here. So if we have a problem, what we have to figure is that you have to know how many states you have, like how many states and how many flip-flops you need to store. But that if the flip-flop is according to the states, right? So if you have a problem, you have to think of like, how many states do we have?